Okay, I got a Pramp interview, and I think, what's it called? Largest, smallest BST key. So pretty much what it means is you have a binary search tree with integers that are all positive, and you're given a target value. Let's just say it's 17. What you do is you want to find the number in this binary search tree that is the largest, smallest than your target, which is 17. So if you look at this, like 20 is bigger, 25 is bigger, so those don't count. 9 is smaller, so that it could be 9. Oh, but there's 12. 12 is bigger than 9, so it could be 12. And then 14 is the largest, smallest, so there's no 15 or 16. So you would return this 14 value. Just a high-level approach, yeah, just with binary search trees, and so order each node, anything left from it is smaller, and anything right to it is greater. So all leaves and nodes right to each node. So when I first thought, yeah, you just got to iterate through the tree and just keep track of what the possible candidate of the uh, the largest smallest is. So we can have a variable like this largest smallest. And if it's not in the, let's just say if the target was 4 and everything was, all the nodes are greater than 4, then you would just return -1. So yeah, you could just say start off at -1 and just traverse the tree. You could do it recursively or iteratively. I tried doing recursively, but that means you'd have to keep an extra variable in your recursive calls. But so it kind of helps working just iteratively. Just use a while loop. So while node doesn't equal none, it's like you said before. You just say is it compare is 17. You compare 17 to 20. If it's greater than, if then the target's greater than, then you so yeah, just say it's 17. It's 17 is less than 20. So that means 20 is greater than, so we don't have to keep track of the largest, smallest. We just move left. Now 17 greater than 9, yes it is. So then we want to move right. But since 9 is less than 17, we want to update largest, smallest here and change this to 9. Right? So, and then we compare 17 to 12. 12 is less than 17. So that means we want to move right to see if there's a bigger one than 12, in between 12 and 17. And then we can update largest, smallest to be 12 now. So now we have 17, and is that less than 14? Yes, it is. So we can update it. And then we move right. So, but since there's nothing here, your node's going to equal none, and that's when you stop. It would break your traversal of your binary search tree, and then when that's done, you just return largest, smallest, which would be 14. So yeah, just say if this was 24, target was 24, you would move 24 is greater than 20, so you set largest on 20. 24 is less than 25, so you move left, but there's no left, and that would break the iteration, the while loop, and then which you would return 20. So that in code, it's not that many. Instead of largest, smallest, I have result here. Let's just change this to yeah, never mind, it's going to break my code. So like you said, you just set it to -1, and then your current node is just the root node you're given at. Right now I have a class node and a binary search tree. So you just, binary search tree has a method saying find largest, smallest. So this method is not outside of binary search tree. It's actually a method attached to the binary search tree class. So you set the current node to the root, and then you begin your traversal. And while there is a node, like you said, if it's less than, you got to update the result current node value to this since it's smaller than the target. This is good. And then you just reset the current node to going to the right and see if there's a bigger, smaller one. If it isn't, if the target, we should rename this target. I kind of like target better. If current node is less than the target, or if it's greater than the target, then we just want to move left, and that's all. And since it's greater, we want to keep track of the result because that's not what the largest smallest. We could do that. Like the inverse of this would be find the smallest largest. Then we essentially move this line 41 down to line 44. Yeah. And then, so yeah, and then this while loop will exit, and then you just return the result that you found. And yeah, and that's it. And then space time complexity, since this is binary search, it's log n time. So that's pretty awesome. And then space complexity is just constant time, since we're only keeping this track of this result. It doesn't grow at all ever. So, yep, that's it. Well, then I can run it here. So like, here's this binary search tree, like the 17 example. This would be, be 14, right? So it's this tree as we got. So it's just now we want to do 7. It should return 5, right? So let's just do 7, which returns 5. Yep. Now let's just say we want to return 4, which should return -1 since there's no nodes in here that are less than 4. So this should return 1, or -1, which it does. And then like 22 should return 20. Yep, see. That's it.